Okay, so hello again and welcome to Principles of Reinforced Concrete. And for today's meeting, we would be discussing about this design problem. So in this problem, we would be designing a square column for the given concentric axial loads, and we would be aiming for gross steel ratio of approximately 3%. So what that means is that our goal is for us to have a rho g be equal to 0.03. Okay, so for our F prime C, that is to be 30 megapascal, and for our Fy, we would be using 415 megapascals. And we would be having these given concentric loads. So when we say concentric loads, it means that they are acting directly at the centroid of your section. So with that, we will be making use of this approach. Okay, so when we are to deal with this kind of problem, the first thing that we will be needing to do is for us to get the value of Pu. So with that, Pu maybe, so the value for your Pu may either be 1.4 dead load or 1.2 dead load plus 1.6 live load, because we only have these two. But for example, that we would be having wind loads and earthquake loads, that is to be another problem or another method, or we would be introducing another load combinations. Okay, so proceeding. So just looking at the calculator, so since you are already familiar with this method, so for the first probable PU, that is to be 1.4 times dead load or 1.4 times 700, and that is to be 980 kilonewtons. And as for the second one, that is now to be equal to, so 1.2 times 700 plus 1.6 times 1270. So that will now give us a PU of 2872 kilonewtons. And as per these two values, we can say that this one is to be more critical. Thus, that is to be the value for PU that we will be making use in our problem. So I will just be writing them here. So PU is now to be equal to 2872 kilonewtons. Okay, so I would be erasing this for us to have space. Okay, so what is to be the next thing that we will be doing? So our basic design principle for UST is that the value of our phi Pn, or that is to be our design strength, that should be greater than or equal to our required strength Pu. So with such, our phi Pn should be greater than or equal to 2872 kilonewtons. But for us to check for the let's say most economical section, we will be making use of the minimum Pn. So with that, this should be equal to. So when we say it is to be equal to, so this the value for our Pn here should be the most economical one, or the section that we will be designing is approximately equal to 2872 kilonewtons. So there. Okay, so for the value for our phi Pn, this is now to be equal to, so from the previous meeting, so going to this slide, where is that? So going to this slide, it may either be this one or this one. So if it is to be laterally tied, we will be making use of this. And if it is to be spiral, or if it would be spiral or in this manner, sorry, the value for your VPN would now be this one. And since we are to deal with a square column, this by default is to be a laterally tied column. Okay, so if it is to be laterally tied, our value for phi for laterally tied concentric columns is to be equal to 0.6. So this is to be for the value for phi. I mean 0.65, I should say. And as for the value for your Pn, so the value for your Pn is to be equal to, so 0.8 times 0.85 Fc prime times the area of the concrete, and the area of the concrete is equal to the gross sectional area of the whole section minus the area of the steel. Then, okay, so after that, we would be adding the strength of the steel. So for the strength of the steel, that is to be equal to AST, or the area of the steel, times Fy, which is to be the strength of the steel. Okay, so as simple as that, let us now solve. So for the value for VPN, we are to assume that it is to be equal to our PU. So with that, this is now to be equal to 2872 kilonewtons. But take note, guys, that your answer here is to be in terms of newtons, because your F prime C is to be equal to newtons per millimeter squared. And for your cross-sectional area and your area of steel, that is to be in terms of millimeter squared. So if you would be multiplying them, you would now be arriving at an answer of newtons. So with that, the answer here is to be in terms of newtons. But for our factored load, we have, what do you call this? We have solved for it in kilonewtons. So with that, it is better. I mean, there is no other way than to convert this one. So times 10 raised to 3 for it to be converted to newtons. So newton per kilonewton. So kilonewton would now cancel out. Or let's say that if you want to retain the kilonewton unit here, you can also convert this into kilonewton. So instead of multiplying this factor here, we can multiply this factor here. So they will just be the same as long as you do not, as long as you do not do, as long as you don't convert both sides simultaneously. So just convert one side. Okay, so moving forward, so this is now to be equal to, so 0.65 times 0.8 times 0.85 times F prime C, and our F prime C is to be equal to 30 megapascals. So 30 times AG minus AST plus AST FY. Oops. AST times FY, and our FY is now to be equal to 415 as given in the problem. So 415. Okay. So as you can see, we cannot solve for this right away because we still have two unknowns. So we have AG here and we have AST. So in order for us to solve for this equation, we must have only one unknown. And if we have two unknowns, we must have minimum of two equations. So since we have two unknowns, let's create a new equation for us to substitute here and for us to solve for AG and AST. Okay, so looking at the problem, it is said here that we are aiming for a gross steel ratio of approximately 3%. So once again, our rho G must be around 3%. Okay, so with that, since our rho G is approximately 3% or 0.03, our rho G is actually equal to, so this is just to be the steel ratio, that is to be AST divided by the gross sectional area. So with that, if this is to be our equation, so erasing this and substituting 0.03, we can actually cross multiply this. So cross multiplying, it would give us an answer of 0.03 AG is equal to AST. So you already have equation number 2. So if this is to be equation number 1 and this is to be equation number 2, we can now solve for it simultaneously. So what I would be doing here is that I would be substituting the value of AST as 0.03 gross sectional area. Okay, so with that, I would just be copying this to our next slide since I do not have any space anymore. Okay. Oops. Okay, so rewriting this. So AST is equal to 0.03 AG. So this is to be my equation number 2. Okay, so moving forward, so I would now be solve equation number 1 by substituting equation number 2 in equation number 1. Okay, so we would be substituting equation number 2 in equation number 1. So with that, this is now to be equal to, so once again, I will just be copying this for me not to rewrite them. It is just that for your AST, so for the value for your AST here, we would now be substituting equation number 2. Okay, so wait. Okay, so this is now to be equal to 0.03 AG and 0.03 AG. So with that, guys, since we already have, since we only have one unknown, we can now solve for it. And you can solve for it manually by algebra. And since I already have my calculator here, I will be making use of technology to my advantage. So 2872 times 10 raised to 3. This is to be equal to 0.65 times 0.8 times 0.85 times 30 times alpha x. So this is to be the value for my AG minus 0.03 times alpha x plus 0.03 times alpha x times 415. Okay, so shift solve. My answer here would be 148529. So AG is now to be equal to 148,529.7008 millimeters squared. So what this means is that if you would be having your square column, the cross-sectional area of it, so the entire area of it, should be equal to 18529.7008. So with that, I will just be copying this once again. So where can we place it? So here. Okay, so once again, in our problem, we are to have a square column. So as you know, you already know the area of a square, and the area of a square is to be side squared. So let's say that x is to be equal to the side. So x squared should be equal to AG. So with that, x squared is to be equal to 148,529.7008 millimeters squared. So solving for x, so we would just be getting the root of the whole equation. And with that, our x is now to be equal to, so square root of answer. So our answer should be 385.3955 millimeters. Okay, so there, and I would just be erasing this. So let's say that this is to be our certain section. So for a moment. Okay, so let's say that that is to be our section, which you are seeing here. So I would just be I would just be moving them here. Okay, so there. Okay, so that if that is to be our section, so I have arbitrarily placed longitudinal bars here for you to see what it would typically look like. So with that, guys, the required dimension for our column is to be 385 point, let's say 4 mm by 385.4 mm. So once again, theoretically, that is to be the minimum required. However, in actual construction practices, it is very hard to lay out this amount of length. So with such, since you are already, since you will be engineers soon, and since you are, since you should consider construction project management, it is better for us to lay them out or to assign a certain section that is to be divisible by 25. So this is just to be a rule of thumb. If you want it to be divisible by 5, so let's say if you want this to be rounded up to 390, so it will be up to you. But once again, by my rule of thumb, it is better if you would be rounding them up to the nearest 25 mm. So with that, guys, I would be rounding this up to 400 mm. So once again, nearest 25 mm, and that is just my rule of thumb. So with that, I will be assigning 400 mm by 400 mm. Okay, so since we are already done with AG, so we will now be solving for the area of the steel. So what is to be the area of the steel required here? Okay, so take note, guys, that we already have a new value for area of cross-sectional area, since we have rounded this up to 400 instead of 385. So with that, guys, I will now be resolving for this equation. So I will just be copying this once again. Spoiler alert. So, okay. So, with that, guys, since I already have the value for my AG, which is the new, actually wala pa. So, let us just solve for the new AG. So, new gross sectional area, this is to be equal to, so 400 mm by 400 mm. So, this is to be equal to 160,000, I think, millimeters squared. So, confirming in the calculator to your left. So, 400 times 400, that is to be equal to 160,000 millimeters squared. Okay, so substituting known values, so this is now to be equal to, so 2872 times 10 raised to 3. This is to be equal to 0.65 times 0.8 times 0.85 times 30 times 160,000 minus AST plus AST times 415. So once again, I will be making use of the shift solve function of my calculator. So 2872 times 10 raised to 3. This is to be equal to, so 0.65 times 0.8 times 0.85 times 30 times 160,000 minus alpha x plus alpha x times 415. So shift solve, my answer here is to be 3,704. So our AST is now to be equal to 3,704.95 millimeters. So this is now to be the required steel area for my particular column. Okay. So the next thing that we will be doing here is that we will be solving for the number of free bars. So with that, guys, so for us to solve for the number of free bars, so number of RSB, that is to be equal to the total steel area or the total required steel area divided by pi over 4 times the diameter squared, so dB squared. So basically, the total area divided by the area of one steel. Okay, so with that, since it is not given in the problem what diameter that we will be making use, so I will just be comparing the different diameters. So I will just be making a table here. So let's say that this is to be the diameter. And this is to be the number of pieces. So let's say that we will be comparing 12 mm, 16 mm, let's say 20 mm, 25 mm, 28 mm, 32 mm, and etc. But I think let's stop with 32 mm. Okay, so looking at the calculator, I will be rewriting this equation. It's just that AST is to be equal to 3704.95. So 3704.95 millimeters squared divided by pi over 4 times dB squared. Okay, so looking at your calculator, this is now to be equal to, so 3704.95. Sorry. So pi divided by 4 times dB squared. So our dB is to be, so it is to be unknown yet. So I would be pressing alpha A. So there, and what I would be doing is that I would be pressing calc for every time that I will be solving it, since we have different diameters here. So this is how it works. So I would be pressing calc, and the calculator will ask me what is to be the value for your A. So I will be trying the first one first. So 12. So with that, it means that in this, if you would be using 12 mm diameter, we are required to have 33 pieces. So guys, round up, because we cannot buy a fractional part of steel, of course, of a steel section. Okay, so for your 16 millimeters, you are required to have 19 pieces. For our 20 mm, we are required to have 12 pieces. For our 25 mm, we are required to have 8 pieces. For our 28 mm, we are required to have 6 pieces. And for our 32 mm, we are required to have 5 pieces. So, tama ba linagay ko? So, 32 pieces. Okay, so it will be up to you on what diameter that you will be making use here. So, you can either make use of 20, 25, 28, and etc. And in this video, maybe it is better if we would be making use of our 25 pieces diameter rebars here. So in the example notes that I have provided to you, so I have chosen 28 mm there. But take note guys that if you would be making use of 28 mm, oh by the way, this is not, so wait, so 28, so this should be 7 pieces I should say. So this should be 7 pieces. Okay. Okay, so once again, if you would be making use of 28 mm, and since this is to be our section, for example, it is very hard to um lay out 7 pieces of rebars because that is an odd number. So it is better for for laterally tied columns to lay out even numbers. So with that, if we are to make use of 7 pieces, so for example that this, I mean the bar diameter that is to be available in your local or in your hardwares is to be 28 mm, we must round this up to 8 pieces. So there, but since it is 8 pieces here, if you are, I mean, if you have the freedom to choose, it is better, and I think it, I mean, it is more economical for you to choose 25 mm. So once again, this is to be by your judgment. Okay, so let's say, so this is just for an example. So for example, that the only diameter that is, I mean, the diameter that is available in your local is to be 28 mm. So for example, the 25 mm is not available in your local. So once again, we will be making use of this. So our section would now look like this, and we will be having 8 pieces of diameter 28 mm RSB. So this is if this is to be the only available, I mean, if this is to be the available diameter in your hardware. But for example that you are, I mean, there is to be an available 25 mm, then instead of 28 mm, then 25 mm. But for the, just for the sake of our example, 28 mm na lang gamitin natin. So 28 mm. Okay, so basically we are already done with its requirements for it to hold this amount of concentric load. So the question is, are we done? So basically not yet. So the next thing that we will be making, I mean that we will be doing, so if I am to be copying this to one slide, so for a moment. So by the way, ito pala. So it is already written here. So okay, so now we will be checking if cross ties are required here. So for by cross ties, these are to be your cross ties, if any. So we will be making, I mean, we will now be checking if it is required. And for us to know if it is required, the value for our SC, I mean, if the value for our SC is to be greater than 150 mm or 6 inches, it means that we must provide cross ties. So if we would be if we would be going to this provision on your right, so it is said here that if it is to be greater than 6 inches or 150 mm, we will now be providing cross ties here. Okay. So with that, so nasa na yun. So with that, we will now be solving for the SC or the clear cover for your rebars. So with that, our SC is to be equal to 400. So that is to be the whole dimension minus So our concrete cover here, by the way, is to be 40 mm. So minus 2 times 40 minus, so what is to be the diameter of our DB or our shear reinforcement or our lateral ties? So the thing is, we still do not know. So before doing this, it is better for you to know first what your DB is. So DB for lateral ties. Okay, so how can we know? So we have this provision here. So nasaan yun? Ayun. Okay, so it is better, I think, if I would just be writing here. So in this part of the provision of NSCP, we will be making use of a minimum of 10 mm diameter rebar if we have used 32 mm diameter rebar and below for longitudinal bars, and we will be making use of a minimum of 12 mm diameter rebars for our lateral ties if we are enclosing 36 mm diameter rebars and above. So ayun. And since in this example, since ito ba yung example natin? So, yes, in this example, since we are having a concentric axial load, so meaning that this is to be a concentric column or a column that is subject to concentric axial load, our lateral ties is actually not not much of an issue in a way na we do not have any eccentricity, we do not have any shear. So with that, guys, we are not to design this in shear. So once again, with that, we are only required to put a minimum, so minimum amount of lateral ties. So theoretically speaking, if we are only to be talking about its structural, its structural capacity, yung lateral ties natin, we are actually not required to put. However, guys, during concrete pouring, so if we would be once again pouring the concrete to our formworks, if we do not have our lateral ties, during concrete pouring, our steel rebars might be misaligned. So yun yung gamit ng lateral ties natin. But once again, theoretically speaking, if we are only to have concentric loads here, etong mga lateral ties natin, hindi naman talaga kailangan yan because we do not have any shear. So ayun. So once again, by provision, we must provide them for our main rebars not to be misaligned during concrete filling or concrete pouring. Okay, so ayun. So once again, since we will be making use of this provision and in our problem, we have chosen 28 mm diameter rebar. So if you have chosen 28 mm diameter rebars, it is to be less than 32 mm diameter. So meaning 10 mm, we would be using 10 mm for our lateral ties. Okay, so with that, this is to be 10 mm. But we have two sides, so times 2. And we would also be subtracting the dimension that is covered by your steel rebars. So that is to be 3. So as you can see, we have 3 here. So 3 times the diameter of rebar, 28. So this was already this was already derived in the previous meetings. Okay. So divided by n minus 1, so n 3 minus 1. So with that, our SC is now to be equal to, so looking at the calculator to your left once again, 400 minus 2 times 40 minus 10 times 2 minus 3 times 28 divided by 3 minus 1, and my answer here is to be 108. So 108 mm. Okay. So 108 mm, and as you can see, this is to be less than 150 mm. So if it is to be less than 150 mm, or less than or equal to 150 mm, this means we do not need, so cross ties are not required. So cross ties are not required. So if it is not required, so in this one right here, so di na natin kailangan maglagay ng cross ties since it is not required. Okay, so what else do we need? So since we already know the diameter of the rebar that we have chosen. The next thing that we will be doing is for us to check the spacing required. So with that, guys, I would just be erasing this first. So let's say that this is to be your column. And let's say that these are to be your rebars inside. So these are to be your rebars. Of course, they are to be enclosed with lateral ties. So this is to be your lateral ties. And for these lateral ties, so since that is to be our lateral ties, of course, they must be spaced equally. So for this spacing, and this spacing, so we would be solving for this spacing. And let's say that those are to be the spacing S. Okay, so for your spacing S, we would be making use of this provision. So the clear spacing should be at least 4/3 diameter of the aggregates. So this is to be the minimum. And as for letter B, so the center to center spacing shall not exceed the least of 16 dB or 48 dB. So with that, guys, this is now to be your maximum. And it is not included here, but we must also take note that the other maximum should be 300 mm. So aside from 48 dB and 16 dB, we must have 300 mm as our other limit. Okay, so with that, I will be reducing the size of this. Okay, so once again, for our minimum, we do not need to check for this any longer because since we are theoretically not required to provide this, so once again, theoretically it is not required, but in practicality, they are required just for it to hold the longitudinal bars. So with that, guys, dun na tayo sa maximum mag-base. So we will be basing our answer to the maximum. So the first probability for our maximum, that is to be 16 dB. And for the second probability, probable max, that is to be 48 dB. And for 3, this should be 300 mm. So if you're asking yourself, isn't it automatically that this one is to be less than this? So not quite, because this dB here, so as seen here in this provision, the 16 dB here, so the dB that we will be making use here, is to be the diameter of the longitudinal bar. And for 48 dB, the dB that we will be making use here are to be your tie bars. So with that, guys, so for this 16 dB, so this is to be equal to 16 times, so what is to be the bar diameter that we have chosen for our longitudinal bars, that is to be 28 mm. So 28 mm. And as for this, so 48 times, so what is to be the lateral tie or the diameter of the tie bar that we have chosen. So a while ago, we have chosen 10 mm. So 10 mm. So solving for this, so 16 times 28, this is to be equal to 448 millimeters. And for this, so 48 times 10, that is to be equal to 480 millimeters. And you do not need to solve for this, so automatic 300 mm. Okay, so the maximum spacing that you will be choosing here should be the spacing that if you would be choosing it, all of the other two shall be it should be compliant with the other two. Okay, so what I mean here is that if you would be choosing this, make sure that this provision or this limit will satisfy both of this. So with that, we will be making use of 300 mm. So do not get confused. So we will be this is to be the maximum spacing, but for the maximum spacing, but if we are to choose the maximum spacing, it does not mean that we will be choosing the highest value, because if you would be choosing 480 mm, so if that is to be the case, or if that is to be the spacing that you have chosen, it means that it is to be, this is not adequate any longer, because 480 is to be higher than 448. So if this is to be your maximum, hindi na siya adequate as well as for this. But if you would be choosing 300 mm, so let's say that you have chosen 300 mm, so 300 mm is to be less than 480 mm and 300 mm is to be less than 448 mm. So what that means is that if you have chosen 300 mm, provision number 1 and number 2 are satisfied. So once again, if you have chosen 480 mm, provision number 1 and number 3 will not be satisfied. And if you would be choosing 448 mm, 480 mm would be satisfied, but 300 mm would not be satisfied because it is to be larger than 300 mm already. So with that, 300 mm would now govern. So for our summary, so our column will be, we will be making a saw 400 mm by 400 mm. For our reinforcing steel bars, we would be making use of 8 pieces, diameter 28 mm RSB. So once again, this is to be your choice. So once again, this is to be your choice. Okay, and as for the cross ties, so no need for cross ties. And for your lateral ties, so DB for lateral ties. So by the way, we'll just be writing it this way. So lateral ties. So DB is to be equal to 10 mm. So we have chosen 10 mm a while ago. And for the spacing for your lateral ties, this is to be equal to 300 mm. So this is to be our answers for the design problem of our short column, which is to be concentrically loaded. So there.